angles. And how many angles would make sine 1/2? I don't right now care what angle it is, but how many angles would make sine come out to be 1/2? That might be a strange question, I don't know. The answer is more than you think, maybe. Huh? Infinite. Any angle that is, what did I just say? Sine theta equals 1/2? Any angle that is coterminal with pi over 6 or 5 pi over 6 will make sine 1/2. And there's an infinite number of them. I think I did kind of sneak this in your brain a little bit yesterday. Let me do this real quick. Ethan, did I give you a copy of that quiz, Mr.
Yeah.
Yes, okay, good. Alright, here's the practice final.
Do you know when it is?
Huh?
Do you know when the final?
Do I know when?
Yeah.
No, we're just gonna have to guess and hope. Sorry, Ethan, I made that there. That it's on the syllabus, it's on the homework sheet. It's 2 days next week. I'm sorry, not 2 days, that's my 176. When is our final? Next Wednesday, good. Yeah. So this Thursday, let me put this up here again. Today, finish up trig equations, go over section 2.6 finally. This is the kind of stuff we'll do in section 2.6. Practice final given out, I just did that. Tomorrow is the first day of review for the final. So tomorrow come with, tomorrow what I'm gonna do is, I think I already told you guys this, we're gonna have group work on older material. And the reason I want to do that tomorrow is over the weekend, you'll be able to attack the practice final with some fresh review of that stuff. And then come Tuesday, you'll maybe have more questions ready for when I just open up the review to whatever you guys want to talk about. Okay, there's a method to my madness every now and again. Most of the time it's just madness. Any questions about what our near future looks like? This Thursday, tomorrow is the first review. Next Tuesday, second review day. Wednesday's the final exam. Thursday, in terms of our class is done Wednesday, so don't come here on Thursday. You'll be lonely. Okay. Okay, is everybody okay with that? Any questions from homework? You guys have any questions from homework? Is anybody doing the homework? Anybody? You're like, why start now, Jeff? That's a good point. Okay. Oh, let me turn this on.
I did have a question.
Yeah. Okay. I'll give you a second to find my marker.
It was question 27.
Oh boy. Oh boy. Everybody just hang tight while I remember which keyboard works. There we go. And I remember my past story. Oh, thank God, that was quick. Wow. So you said, I'm sorry, which section again?
9.1, question 27.
Whee. All right, so this is the first place where we had to verify identities. And I'm really sorry, Kevin. You said which number again?
27.
27, okay. Oh, okay. This section is weird. I agree with you. So this one says, simplify the first by writing it in terms of the second. So they want cotangent x, but in terms of sine x alone. So what is cotangent x? Just directly, what is cotangent x in terms of other trig functions?
Cosine over sine.
Yeah, cosine over sine. Now, have we got it written only in terms of sine yet? What do I want to get rid of? Cosine. Now, how are cosine and sine related? Which thing do we know relates cosine and sine sort of directly? Maybe there's some squares in there. I don't know. Yeah, Pythagorean identity. What's that one say?
Sine squared x plus cosine squared x equals 1.
So if I solve this for cosine, can I plug that shit in here and have only sine?
Yes.
Okay, that's the point of those problems. They're saying take the first dude, rewrite it so it only has the second dude in it. So they gave me cotangent and the second dude sine. I'm like, oh, okay, I've got to get it all the way so only sine shows up. How do I solve this for cosine?
You subtract
That's insane.
sine squared x.
And then I got to do one more thing.
Square root plus or minus.
And this, why am I doing the whole problem? I don't know, Jeff. You're done though. This you just plug there. There you go. Freebie. I couldn't stop myself. Does that make sense? I mean, the instructions on the problem, that set of problems is a little weird when you first see it. You're like, what do you want from me? Problem? But that's literally all it wants is just rewrite it, but then rewrite parts until you only get this one function left. So now if I plug that in there, the only function I see is sine. My sine is the only trig function I see. Anything else from homework stuff?
Yes. 9.2.
Oh, that mouse doesn't work. I love it. Sorry, I gotta remember where I am. So 9.2 number 21. Okay. So given that sine A is 4/5 and cosine B is 1/3, and you're like, great. With A and B both in this interval, 0 to pi over 2. So what does that mean? What's another way to say that?
Quadrant 1.
Quadrant 1, first quadrant. Find sine of A minus B. Oh, okay. This one's kind of fun. All right, let's look. Can you guys take a minute? Can everybody just take a moment and rewrite this in a way that it could potentially use that information, right? So sine of A minus B. Can you rewrite it? So I don't want the angle, I don't know shit about the angle A minus B. I know some things about the angle A and the angle B. How would I rewrite this?
Sine A cosine B plus
No. So
sine
I don't know why they're suddenly using lowercase, but we'll be okay. Sine's the nice guy?
A. Yeah. Sine A cosine B.
Yeah, so they take turns, keep it the same.
Sine B.
Now notice, what did they tell me? Did they give me enough information? They told me where to go. There it is. Sine A and cosine B. So they told me what sine A is, and they told me what cosine B is. Why is that not enough information? Yeah. But if you know sine A is a ratio, how do you figure out what cosine of A is? What is it in sine A equals, what was it, 4/5?
Yeah.
4/5, okay. So if I know sine A is 4/5, how do I figure out what cosine A is? There's two different ways you can do it. You can either do it the first way we did it, or you can do it with an identity.
5 squared minus 4
Do it again?
5 squared minus
Oh yeah, so you can draw a triangle, label the size, use old Greek dude. Yes? Or, didn't we just do a problem where if we knew sine, we could figure out what cosine was? I could use a Pythagorean identity directly. So what you just said, I want everybody to pick up on this. This happens all the time in mathematics. You just said use Pythagorean identity, but you said use the Pythagorean theorem on the triangle.
Right.
So that's using that on that piece and then putting things together. Or I could use Pythagorean theorem on a higher level as an identity between sine and cosine. Sine squared plus cosine squared equals 1.
Right.
Both of them will come out with the same answer. Can you say all of that again, Jeff? But this time, choose English. Okay. Could I draw a triangle with angle A in it? What sides are what? Y is 4. R is 5. So we already know this is what? 3. So then what's cosine A? Yes, so this would be 3 over 5. Or I could do 1 minus sine squared equals cosine squared. So 1 minus 16/25, which is 9/25. So cosine A is 3/5, and I choose the positive one because it told me I'm in the first quadrant. Didn't I get 3/5 two ways?
Yeah.
Okay. Now, of course, in this problem, I'd rather do the triangle approach, yes? That's a lot less work. Because it's such an easy set of numbers, I didn't really have to do the Pythagorean theorem. This is applying the Pythagorean theorem at a higher level.
So if there's like not easy numbers, you probably wouldn't do that.
Yeah, we could do this and that's pretty quick then. Yeah. Either way, they both work. I normally do that way, to be honest. It's normally quicker. Yeah. I don't know if you guys are with me. You got 2 different ways you could do that. Now, why the shit did I just do this? That's a really good question. Because I needed to know cosine A, don't I?
Yeah.
And now we do. We know cosine A is 3/5. What else do I still need to know?
Sine B.
Sine B. Oh man, if I only had a way. Now we got 2 ways. We just do that with what they told me cosine B is. I draw its triangle, or I use this dumb thing again. Yes?
Yeah.
So what we just did was we did this. And this happens all the time in mathematics. I wrote an equation for the question. And then I stepped back and I said, all right, that equation I just wrote, what parts of it do I know and what parts don't? Oh, I don't know these. Okay, how do I get these? So I know this is the question they're asking me. I know this is how I get what they want from me. And I know what I know and I don't know. I'm like, oh shit, how do I get what I don't know? Right. Okay, that happens so often in math. If you just write the formula for what they're asking you and step back and go, how do I get what I need? Maybe. Okay. You guys look appropriately excited. Anything else from homework stuff? Kevin's all tapped out. And everybody else never tapped in. Okay. So let me. Wait, I don't want to go back there. So let's do this. Let's do. Oh yeah, we did get a little bit of this, didn't we? I thought we did, maybe not. Okay. Let's remember the kind of problem we did yesterday. So if I had cosine theta is -1, and I want the answers from 0 to 2 pi. So this one's an easier one because it's an extreme value for cosine. How many angles make cosine -1? Well, what angle makes cosine -1? What angle makes cosine -1? Hit it with me a better choice of units. Pi, right? Cosine of 0 is 1, cosine of pi or 180 is negative. Yes? Is there anything else in between 0 to 2 pi that makes cosine -1? No. You guys with me? How many places make cosine 0? So this would be the answer. Yeah. This would be the answer. How many places make cosine 0? Pi over 2 and 3 pi over 2. I love it. So those would be the answers. Okay, so, and then the only way I can make this a little more complicated is to do something like cosine of 2 theta is, do I want to do that one? Maybe. Cosine of 2 theta, let's say, is, let me think ahead of time. Yeah, okay, is 1/2. do we have an identity for this?
15.
We have 3 identities for cosine 2 theta, yes? Does anyone remember the double angle formula for cosine? There's 3. There's a main one I kind of start with. Yeah. So one option is cosine squared theta minus sine squared theta. Do you guys see why I might not pick that one? But that's a good place to start. Why might I not pick that one? Because it's gross. I can't solve. Now I still have 2 unknown bits. Yes?
Because we're getting sine involved and
Yeah. We're getting sine and cosine involved. I just want one of them because then I can solve for it. Is there another way to write this that only has one trig piece?
2 cosine squared theta.
Yeah. Yes?
Yes.
Yeah, this will work. All right, let me stop for a minute. So, when I'm solving trig equations, some of them are going to be very direct. Cosine theta equals rad 2/2, and then you just have to think to yourself, what angles make that happen? Some of them are going to involve something more akin to algebra. Some of them are going to involve trig identities. Yes? I am going to show you something about double angles, going to make it easier once we get to this next piece of solving trig equations, but for right now, I need to break it down into just theta. Can we solve for cosine theta? Add 1, it's a good first start. Divide by 2. Square root. Plus or minus, yes? Does that number look familiar? Do I know the angle? Now look, it's plus or minus, so what quadrants can I be in? Which quadrant specifically makes cosine positive or negative? All of them. So I'm in all of them. So let's just get the base answer. What makes cosine rad 3/2? When is cosine happier, right? This is a bigger output, so when is cosine happier? What angle makes cosine big? Yes, close to the x-axis. That is the one that's in the first quadrant. Can you guys, are you at the point where you could just tell me what that would look like in the second quadrant? So pi/6, reference angle here. What about the second quadrant? Let me see from your perspective. This is the first quadrant. This is the second quadrant. What would it be in the second quadrant? No? That'd be pi/2, that's here. What is pi/6 short of a full pi? Yes? So visually, here's what I'm doing. One answer is pi/6. That makes this triangle here, yes? I want that same triangle, but I want it in all the quadrants. So how short am I of a full pi over here?
5 pi/6.
So that would be 5 pi/6. Then I want to go pi/6 past this, yes?
7 pi/6.
7 pi/6. And then I want to be short pi/6 again of 2 pi, which is 12 pi/6. So what's pi/6 short of 12 pi/6? 11 pi/6. Oh my God. So it's because of the square that made more answers. But if you back up, it's because of the 2 theta that made more answers. Let me really, really make you like me a lot. What does that do to the graph of cosine? Nope, the amplitude didn't change for it because there's no number out front.
Oh, it's stretches.
It does one of those 2 things. What was the original period of cosine? 2 pi. What's k? Oh yeah, Phil's here.
Yeah.
Phil, come on in, but give me just a second.
Yes.
We'll finish this out real quick. What's k in this equation?
2.
2. So what's the new period then? No? So the old period is 2 pi. What do I do with k to get the new period? Divide by 2, yeah. So what's the new period? Pi. So cosine normally took 2 pi to do all of its stuff. Now this one is going to take pi to do all of it. So it's going to hit 1/2 more. So we're going to see in a minute more of these, but whenever I have a number in front of theta that's bigger than 1, I'm going to get more potential answers in my final collection of answers. All right, so Phil Blanco is, we're going to take a little break from lecture for just a second. Phil is an astronomy and physics professor. He's got a new course that thankfully we have now here at Grossmont, and he requested just to get a few minutes to let y'all know some basics about this possible new course you can take. Go for
Sales
it.
pitch. Can you zoom out to show more of it?
I guess so.
Very kind.
Thanks, Phil.
Focus.
It will.
Yeah, so I'm Philip Blanco. I'm an instructor in our Department of Physics, Astronomy, and Physical Science. And first of all, you guys made the right decision by taking this course, which is a pathway to calculus. Don't let anyone tell you that it's basic mathematics. What you're doing is fundamental mathematics. We in physics were so glad when this course was created, because we have students who've done calculus 3, and yet they can't rearrange an equation, or they can't figure out what a 2 in front of the theta actually does in terms of making things whirl around. So they've just been doing kind of coasting on doing this cookie cutter stuff. But with Professor Waller especially, you guys have done the right thing taking this course, because those foundations will carry you through. It's like making a secure foundation, and then you can build on top of that. Whereas I think some of our calculus-based physics students, their foundation is kind of wobbly, so they're kind of doing this. So, Math 171, assuming you pass it, you're all going to pass, nod your heads, right? Assuming you pass it, that provides the prerequisite for taking a STEM class, which again is fundamental. Is anyone here thinking about possibly being an engineering major? Possibly aerospace? Kind of looking into it? So this is actually a great way to dip your toe in. This course that we just created is to my knowledge, is the first ever community college aerospace course that transfers to a real STEM major required class at San Diego State. Aerospace Engineering 1, 2, 3 is taken by all of their majors, and in fact they have juniors and seniors that haven't taken it yet. They've got to take it before they're allowed to graduate. But you'll have a lot more fun taking it with us. In fact, we're going to get SDSU students to come here. And we're going to have fun. So let's see, all the labs will be hands-on. We're going to be launching rockets, flying planes, water-powered rockets, because we're a little bit close to Gillespie Field. We don't really want to have high-powered explosive rockets. But these are cool enough, and the cool thing is, it's the same mathematics. It's the same equation. Can I write an equation on the board? Is that allowed?
Oh, yeah. Do you need a
I
mark?
think I've got a marker.
Yeah, you
Mine
do.
not that good though.
Go for it, man.
The rocket equation. Okay, you probably have a better marker.
Maybe.
Actually, these markers work great in physics, but strangely in mathematics, it's like
Try that
invisible. It's like invisible ink. I don't know why that is.
I won this
Oh,
step
that's
with
much
that.
nicer.
Okay.
Now, this is cool. Rocket equation. It says that we okay with delta for a change in something?
Let's try it.
All right, delta V, which is your final velocity minus your initial velocity, delta V is equal to the speed of the exhaust coming out of the back times the natural logarithm, log or ln,
Ellen.
ln, the initial mass of the rocket divided by the final mass of the rocket. Cool thing about rockets is that, in a car, when you accelerate, where do you feel that biggest kick in the pants? At the beginning, when you're at a stop sign, or perhaps later on? Beginning, right? You feel that oomph at the beginning. If you hit the gas at 70 miles an hour, you get, not so much. The cool thing about rockets is that they're constantly losing mass. So as the force of the exhaust stays constant, but it's pushing on less mass, rockets actually accelerate faster the longer you wait. So the cool thing about them is that the force stays the same, but the acceleration increases with time, unlike unlike other vehicles. And it's the same equation for a water rocket. You get to see the water draining out under pressure, as it is, say, for Elon Musk's Starship that he's launching and crashing in various ways. So we'll be applying the Math 171 material that you learned, like natural logarithms, they covered that, right?
Okay.
We'll be applying that to real world situations. We're going to attach a 3-axis accelerometer to the rocket. We'll measure its performance on the way up, and then you guys will be designing a recovery system, parachute or streamer, because we like to get our accelerometers back to the ground. As I said, we'll be making some model airplanes and flying them around, hopefully in the lower gym over there, which is just about big enough and has the advantage of no wind. We'll also be working with our drone program, and so we get to borrow one of their drones and we're going to science the heck out of it and test it and see if we can improve the amount of mass that it's able to lift. And also we'll look at things like propeller noise, because if you're a wedding drone photographer, you want to have a nice quiet drone. You don't want to have something in the wedding video going all around the place. So let's see, I have flyers. I have to get them out if anyone is interested. We also offer other courses for STEM majors. Physical Science 120 is MATLAB programming, and that's completely asynchronous online, so it cannot interfere with your schedule in any way. And Physical Science 210, you do need to take some physics prerequisites for that one's electric circuit.
Phil, did you get GE for this or no?
It does. Unfortunately, no.
Okay.
And it wouldn't work anyway because
I didn't think it would, but-
it's half lecture, half lab.
Okay.
So no. But this is a real STEM major course, but you don't necessarily have to commit to being an aerospace engineering major. If you just want to dip your toe into STEM, this is an awesome way to do it, because you'll have fun. You get to take home all the things that you built, or more accurately, you get to take home the wreckage of the things that you built and flew. Zero textbook cost. We're going to provide you with some professional grade software that you can put on LinkedIn that you're now an expert in free flyer orbital mechanics software. So at least virtually, because we can't afford to do the real thing, but virtually you can fly to the moon and back and around the planets as well. And you can get a software certification for that as well. So who wants a flyer?
Nice.
All right. Yeah, it's a sweet deal. And I'm going to be spending most of the summer trying to figure out, let me see. I've got a combination of flyers and actual syllabi. I'm just not organized. I'm an absent-minded professor today.
That's me every day. I want to tack something on, by the way.
Some of you get a flyer, some of you get a syllabus.
Phil's doing a great job of letting you know that this class will use the stuff we've done in this class. But when you go to calculus, what Phil was talking about
If
the
you
mass.
want, if you want, you can snap a picture of the flyer.
Yeah. The mass. I'm going to put it up on our canvas too.
Oh, thank you.
As the mass changes, the equation of motion is dependent on that mass.
Thank you.
So to really accurately determine the equation of motion of that, you're going to need calculus, because calculus handles when variables are changing throughout.
Yeah.
So as you learn more math, so you can do this using the math you know at the end of this course, but as you learn more math, you'll be able to do more, which is the coolest thing in the world for a student to go, I can do this, and you do it, and then you learn a little more math, and you're like, oh crap, I can do more now, I can understand more now, I can set up the equations. Yeah.
Right. But the simple, you always have to start out with the simplest possible model. At least in science, we're trying to simplify things. So we're not worrying about every single atom that comes out of the back of the rocket. And initially, we're not worrying about the changing exhaust speed. And it turns out, simple, you can get away with a lot. You can describe things quite accurately to within a few percentage points using the simplest possible model. And that's what we have to do in science. We have to decide, do we spend a long time trying to get that extra 1 or 2% worth of accuracy with a whole lot more complexity and the chance of making mistakes, or do we go with the simple thing? I'd say for unmanned rockets, keep it simple. If you've got people on board, like Artemis, when they did that spot landing just a couple of months ago, that's where you got to spend the extra effort. But those guys started out, I can guarantee NASA started out with this when they were designing the mission. Just a logarithm.
Yeah, it's crazy.
It's crazy that nature lets you get away with, or at least that nature lets you approximate things. But you can do a lot. You have to be smart, though, how to simplify things.
Yeah, you could assume your ropes are frictionless and massless and get away with a lot doing that. It's crazy.
Oh, we have a special account with the massless pulley store and the frictionless rope store. So
it's nice.
we just buy them. I'm kidding.
No, I thought you were gonna say, oh, we
Yeah.
have a frictionless rope in the.
We do sort of, yes, we have a bunch of massless.
But it keeps, it's just always moving, it just won't.
Right. So, so this is a great way to learn those things, to learn how you can make decisions in STEM, decisions that actually work, and you'll be able to compare your predictions with real experimental data.
There's Phil's email.
Yeah.
And he could certainly tell you more information. Do you know what? Yeah, here. Okay, good. There's the time it's being offered.
Thursdays 2 to 3:50, and I'm going to
One unit.
hours.
It's a great way to kind of feel engineering out.
Yeah, $45 for 1 unit, right?
Yeah. Cool. Thank
So
you.
great way to feel out STEM and engineering and planetary science and all that good stuff as a profession. But you guys already made a good decision by coming. All right. Thank you.
Thank you, Phil.
I'll let you get back to your cosines. we will be using those too.
Thank you.
Hell
All
yeah.
right, well, thank you.
See you, Phil.
Bye.
Thanks, man. Okay. Let's see. Where was I? I almost forgot he was coming. Yeah, Phil is neat. He's been writing some papers he does physics, he does astronomy. And another life that could have been me. I love my math though, so. Where did we leave off? Let's see. Okay, I think the last thing I was talking about was the period. Does that make sense? I really want this to make sense. So like, if I graph a normal sine graph, or was this cosine? It doesn't matter, Jeff. If I graph a normal sine graph, how often does it hit 1/2? Yes, twice. But if I increase the frequency, if I compress it, so from 0 to 2 pi, this only hits twice. But if I compress it, now it's going to hit 1/2 much more often. And then if I do like 3 times theta inside, I'm going to compress it even more, and it's going to hit 1/2 even more. Okay. So I want to get to the place where, let's see, do I want to have you guys... I'm sorry, I'm a little thrown off now. I gotta get back on track. Yeah, okay, beautiful. Perfect. Let me give you a little bit of a background of what we're about to do. Let's start with this. What we just said, sine theta equals 1/2. I'm gonna expand this. So I don't want just the answers from 0 to 2 pi. I want all answers to this. And we're not going to list them because I think earlier, you guys, if I go back to my little graph of sine, if I graph the whole sine wave, how many times does it hit 1/2? Forever. I mean, infinitely many times, yes?
Yeah.
It will just always come back and hit 1/2 over and over again for infinity. So we're not going to list the answers. Oh, holy shit, because if so, my students from last semester would still be listing the answers. So we're going to do it a little bit better way. Can somebody help me figure out the 2 main places where sine becomes 1/2? What are the 2 main angles that make that happen?
30.
Yes, so that would be otherwise known better as 5/6. And what other angle?
5.
Yes, so wherever y is positive and close to the x-axis, so that's going to be an angle of pi/6 and an angle of 5 pi/6. Now, this next part's really silly. This is the silliest part of trig, in my opinion. Did I tell you guys about the parking garage and stuff?
Yeah.
Yes, okay. So you guys might have forgotten. It's okay. I say it a lot. Who listens? If I want to get back to here, how far do I go to get back to there exactly? 360 degrees, otherwise known as 2 pi. Yes? If I add 2 pi, don't I get back here? What if I add another 2 pi? Every single one of those, the devil inside, no, every single one of those will answer this equation, yes? Why? Because they all end up at the same place, which means they all have the same triangle, which means they all make sine 1/2. I can do the same thing for the other dude. So look how we capture this. I could go up 2 pi. I could go up 4 pi. I could go up 6 pi. I could go down 2 pi, 4 pi. Now, how do I make this become 2 pi, 4 pi, 6 pi, I just multiply it, and I think, I can't remember what this book uses. Did I talk about this with you guys yet?
Yeah, yes.
Oh, look at me suck. Look at me forget what I did. I'm sorry, guys. I'm always tired, and I'm really sorry. So I'm going to do the same thing here. I want to do one example, though. Here, before I haven't given you this sheet yet, I don't think. And if I did, I don't know why I have so many left. I haven't given you this one yet. Look at all that. Look at all that writing. Okay. Let's try this. I want to show you. Well, tangent's got its own thing, but just to really make sure you guys understand. What makes tangent 1? Or? No, 3 pi over 4 would make tangent negative 1. You with me?
Yeah.
5 pi over 4. Now, I could, Jeff, stop yelling. I could add plus or minus 2 pi k to each of those, but that's really dumb. And I'll show you why. Why I really want this to be, makes nothing but sense. Is it possible, coming back to this problem for a second, could I start at this angle, add a step size to get to him, and add the same thing to get back?
No.
So I had to do 2 separate lines. Could I start at this guy, add some amount to get here, and add the exact same amount to get there?
Yeah.
So I can pick up all of the answers in one line. And of course, how much is this? So I'm not going to write it like this. I'm going to start at this guy, and I'm going to go forward or backward a multiple of pi. Now, that makes nothing but sense when you stop and think about tangent. What's tangent, period? Pi. So it kind of makes sense. But this kind of thing could happen even with sine and cosine. This kind of thing, whenever it happens, I can write the answer in less lines. Now, if you had given to me this answer, I wouldn't take points off. I'd just say you could write it more compactly. So let me give you this. Let me let you guys work on this. I think I stopped recording when Phil got here. So for this problem, if you need to, you can kind of remind yourself what quadrants you have to be in. Right? You could do that 2-step process we were talking about before. What quadrants would I have to be in for this to be a true statement? Yeah, wherever x is negative, so it'll be in 2 and 3. And then what angle would actually make rad 3 over 2 the answer for cosine? Well, in general, it'll be pi over 6. 5 over 6. So then I would do 5 pi over 6. That's 1/6 short. And then I would also do 1/6 past pi. What would that be? 7 pi over 6. Now you can tell really easily that this is not the same step size as this. That's what tells me I cannot capture the answers in one line. I have to do it in 2. So if I start at an answer, how far do I go to get to another answer? All the way around. In other words, 2 pi. So I'm just going to plus or minus 2 pi k, plus or minus 2 pi k. I think our book puts just plus because technically k can be negative. I like to put the plus or minus in your face because then you remember you can go forward or backward. So let me show you one more trippy example, and then we'll talk about 2b.
So since this one doesn't have lines that are on opposite sides, like opposite.
Yes, I'm with you.
Yeah.
It's not like directly opposite, yeah.
So you don't have just like one way, right? You got
Kick
to
ass.
like through it.
Yes.
Okay.
And that is a shortcut way to realize some situations where you could do it in one line because because the distance between them is the same both ways. The distance between these is very different. Okay. And that's what tells you I need more than one line. Look at this example. What's different about this equation? Squared. How do I kill the square? Square root. I love it. When I take a square root, I better put plus or minus. What's the square root of 1? 1. What's the square root of 2? I don't know. And if I rationalize this, that should look very familiar. I don't know what happened to me. That should look very familiar. Yes. So what base angle are we talking about? And which quadrant could it live in to make cosine positive or negative? All of them. So now watch this. This is so cool. I desperately want you to get this idea. So I know the base answer is pi over 4. And I could be in all. So here's pi over 4. Reference angle in all of them. Now, Ronnie, your realization earlier, do you see how this is directly across from this? But there's something even better. How far are these apart? 90 degrees. Pi over 2. How far are these? Pi over 2. How far are these? Pi over 2. How far are these? Pi over 2. So if I really want you guys to see that. Do you see how the size of the step to get from one answer to the next is the same throughout? So I can capture all of my freaking answers in one line. How much, though, do I step by? Multiples of what? What did we just say? Multiples of pi over 2. Bam. That is the complete picture about how can I know when I can write a bunch of answers in one line. It's literally just, I like your idea, but that only captures like the pi. It's literally just, is the size the same from, the step size the same from one to the next? In this case, totally. 45 degrees is right for that. 45 degrees is going to make that happen more often than not. So, let's talk about this dude. Can you tell me if this makes sense? Do you see over here how we solved for x? All right. I want you guys to solve for 3x. Solve for 3x. What is 3x? And I love when I ask the question, you're like, 7? No. What does it represent? What does 3x represent?
3 times an angle, but
No. 3x is an angle.
yeah.
The cosine of this angle is 1/2. So what could 3x be? Don't say anything. Solve for 3x first. This is good news. Some of you, I don't know if some of you guys were worried about, did we learn the triple angle formula with this guy? If we did, I was very much asleep at that point. Right? I don't know if anybody's worried about that. The fantastic thing about solving trig equations, with what I'm about to show you, I never have to be careful what I'm saying. If I have trig equals number, and I have a multiple of the inside, I don't have to worry about that till the end. I don't have to use an identity, none of that shit. So just take a minute. What angle makes cosine 1/2? Write down the two base answers. All right, let me catch up to you. This, hopefully everybody understands. All I want you to do right now is write down this angle. What would it need to be to make cosine 1/2? So what's one possible answer? What makes cosine 1/2? Don't let the 3 get in your way. Just this angle. This angle.
Pi over 3.
It would have to be pi over 3. Or what other quadrant would make this work? fourth quadrant, so how could you write that angle in the fourth quadrant? Same angle in the fourth quadrant. There's two ways I would accept. To be honest, there's an infinite number of ways, but there's two ways that would make the most sense. Is it pi over 3 short of something?
5 pi over.
Yes. 2 pi, which is 6 pi over 3. So like Trent just said, pi over 3 short of 6 pi over 3 is 5 pi over 3. I would have also accepted negative pi over 3. Because that's the same dumb angle. Now, how do I capture all the answers that 3x could be?
Well, solve for x.
No, how could I get all the things 3x could be? It could be this angle, or I could start here and go forward multiples of something, plus or minus what? 2 pi k. Do you see how I don't give a shit about that 3 right now? I am solving for 3x. That is an angle. I'm solving for the angle 3x. Every step we're taking right now is exactly as if I would have just written x there instead of 3x. I don't worry about the 3 till the end. So of course, what do I put here? That's insane. Now I solve for x. How do I solve each of these for x? I do the same dumb thing.
Divide everything.
Divide by 3. How do you divide fractions by 3 really easily? You put the 3 on the bottom of the dumb thing. That's dividing by 3, yes? So what do I get for the first set of answers? Pi over 9. 9. Plus or minus 2 pi k over 3. And I also get 5 pi over 9. Plus or minus 2 pi k over 3. Now, oh my gosh, Jeff. I'm going to write that again over here. I want to focus on it for a second. I'm going to write these answers again. So we got this. And we got this. Okay. Now, I want to really make sure you understand the concrete reality behind this blurry mess. Go away and then come back again, please. Peas and carrots, thank you. Does anyone understand what this means? What can K be? What this shit is K?
And just how many?
Any
Whole number.
whole number or integer really, but any whole number. 0, 1, 2, 3. Yes? You guys with me?
Yeah.
So if K is 0, what answer do I get here? Pi over 9. If K is 0, what answer do I get here? 5 pi over 9. If K is 1, let me see if you guys can see what I want to do. This is something similar to what we did before with step size and all that business. If K is 1, I want to add these together, yes?
Yep.
So why don't I just, for my own sanity, make them LCD right now?
Oh, yeah.
So if K is 1, what do I get now? Pi over 9 plus or minus, plus, let's just do going forward, yes? Pi over 9 plus 6 pi over 9 is? 7 pi over 9. 5 pi over 9 plus 6 pi over 9 is?
11 pi over 9.
Yeah. So that's the concrete, and of course I could go backwards too, yes? That's the concrete reality behind what we wrote. If I let K be any whole number that I want to, I will get an answer. Every single one of those answers, every single one of those angles makes the equation work. Okay, good. I just don't want you to forget what we mean when we write this. It's really easy to forget what the shit this means. It's just a really quick way to write this entire freaking infinite list of numbers. Not just infinite. It's infinite that way and it's infinite that way. So holy shit.
It's just like domains, right? And I mean, it's pretty similar where we're saying like it could be anything within this
Oh!
range.
Not really domain or range, but literally, have we ever solved equations that had more than one answer? The answer is yes. So like when we had to factor inside each one, we got, so this is an example of an equation that has an infinite number of answers.
Yeah.
So it's not really domain, because we're not just talking about a function, we're talking about what values makes a function become something specific.
Yeah.
And just the stupid way trig functions work, where they're like, here we go, we're doing it again, and it just keeps going forever. This should not be surprising that I get the same stupid answer, an infinite, we're there again, hey look, we're there again. I get the same answer an infinite number of times. So if I want to solve an equation with all the answers, a trig equation, I'm going to get an infinite number of things. But do you notice every time the first step was, what are the base answers? From 0 to 2 pi. Yes? Okay. I like it. Maybe. Maybe? Okay. So, I want to talk about the last new idea. It's not even that new for the semester. Is anybody excited about that? Thanks, Fred. We love Jeff, but we don't want to see anymore. I understand.
Were we not going to do 1B?
We could. I mean, sure. Let's take a look. Here, let's take a look at. You're right, Ryan. Let's do 1B. I didn't purposefully not come back to it. So let's say we want to find all the solutions. This is going to be exciting. Is that 2x? Is that trig function it's in equal to a number?
Yeah.
Let me say this a different way. Do you all see the sign 2x? Is that equal to a number in this equation?
X.
Was cosine of 3x equal to a number in this equation? Yes, 1/2. Cosine of 3x equals 1/2.
Right.
Is this sine 2x equal to a number? No. Okay, good. So I need to do something about that too. I need all my trig functions in my equation. It's a more complicated equation. I need all my trig functions talking about the same angle, or else they're not going to work together. So what do I do with sine 2x then to force it to be talking about the same angle as this guy? Do I have, I don't know, we would have called it maybe something like double angle, because that's twice what I want. Yeah, sine is a nice guy, right? He's only got one option, thank the gods. I really want this understood. If this would have been sine 2x equals rad 3 over 2, we would have done it like we just did it. We would have solved for 2x. The last thing we would have done is divide by 2, because it would have been a simpler equation. This one's more complicated. I'm like, oh no. So then I do have to take care of the 2, get it to become just x. What do I do now? Why can't I divide by sine? In case anyone's considering it.
Because they're not actually like terms.
No, they totally are. I mean, you don't have to be like terms to divide something away, right? 5x divided by 5 is x. I don't have to be like terms to divide and multiply. What can I not ever divide by? 0. Can sine be 0? So if I divide by sine, I could be divided by 0 and not even know it. Right? And you could have mistakenly caused a black hole that swallows Pluto. And then we're like, why does Pluto always get shit on? He was a planet, he's not. And then a black hole that you made killed it. All right. So let's not go down that route. As much as I'd like to see that, that'd be neat. What I do instead will feel very familiar, and I think we've done this before, I thought we did, is I get it equal to 0. Because then what can I do with this side? Now this feels weird because there's nothing squared. So normally when I have just x, when I see squares, I think get it equal to 0 and then factor it. So can I factor this?
Yeah.
What comes out?
2 cosine.
2 cosine.
I don't know.
What do they both have?
Sine.
Sine, yes. So I can take a sine out. And what's left if I take a sine out? 2 cosine x minus sine divided by sine is 1. Did we do an example like this before? Okay. It's okay. We've done one, and you're like, one's not enough, Jeff. I know. This should feel very familiar. You get it equal to 0. We factor it. Once we factor it, what do we do with each factor? We take each factor and we throw them in the nearest trash can. No. How do I solve for x? You're skipping a step. What do I do with each factor? I take sine x and I set it equal to. Well, it's the only way this could be 0 is if one of these is. So either this is 0 or.
So sine is x equals 0.
More than that. So what are the fundamental angles that make sine 0? And when I say fundamental, I mean between 0 and 2 pi. Just one rotation, dear God. What makes sine 0? 0 and pi. Anything on the x-axis. All right, we'll worry about the rest of him in a minute. What do I do with this mess? Yes, this was easy because it was solved for sine. Let me solve this for cosine. Stupid little asshole cosine making me solve. Okay. And then you ask yourself the same question. Why am I here? No. What angle makes cosine 1/2? Pi over? I couldn't hear you, Trent. I'm sorry. 3, yes.
Yeah.
I didn't hear it. I wasn't trying to.
I thought you were saying like I said it wrong.
No, I just couldn't really hear what you said.
Okay.
I was like, okay. And then, or what? Because what quadrants would I need to be in?
Positive, so third,
First and fourth to make x positive, and that would make cosine positive. So either pi over 3 or 5 pi over 3 or negative pi over 3. It's up to you. And over here I got 0 and pi, yes? So what's nice about this? Do I have to write 2 lines, or can I start at 0 and... Yes, I can start at 0, and I can go up or down any multiple of pi. Pi k. Sorry. Every time I write that, I think that. Do you guys even get that?
pi k.
The parquet is the oil. It's dumb. It's an old butter commercial from when I was a little kid.
No.
Some oranges parquet. Parquet. Okay.
I don't know the last
I am sorry. I am sorry. I want to illustrate how old I am continuously. And then for this one, am I able to get this in one line?
Nope.
Because this is way bigger than that. So I just tack on to both of those what?
Separately.
2 pi k. Shut up, Jeff. All right, I'm sorry. So there's the series of generators of angles that make this work. I just use a weird word. Generator just means an expression that when I plug stuff in, it generates what I need. So if I put different values of k, each one of them will generate another angle that works. Okay. So most of the time, you can get away with getting the answers and then just sticking a plus or minus 2 pi k on the end. But I do want you to stop and think, could I get away with doing it in less lines? I really want you to stop and think about that. I am not going to necessarily, that's a very teacher answer, Jeff. I won't take points off if you don't do that unless I explicitly say to do that. So you know I'm going to explicitly say to do that somewhere. Okay. Now, last thing for the semester. And this last thing is kind of like chock-a-block full of different things. Here we go. I want to keep myself going in the right direction. Can you guys remind me, here's an example of what we're going to be doing tomorrow. Can you guys remind me how to solve this thing here? Yeah, no. This is related to something we just talked about a second ago. Do what to this? Yeah, that's true. So what numbers? Sorry, Dylan. I'm sorry, man. Oh man, that sounded so bad. I'm sorry. But yes, we are factoring, and now I just want the numbers that make it work. Yes.
Positive 2, negative 6.
I know it's been a minute, but this is the example I just referenced when we were doing that with sine and cosine a second ago. Factor it, get it equal to 0. It was already 0. Thank you, Jeff. Factor it, take a little nap, and then what are my two answers?
Negative 2 and positive 6.
Woohoo! Okay, so here is a slightly different problem. Let me actually make one that goes somewhere nice. Would you guys like that? Preferably? Yeah. Okay, I'll do that. Okay, I'll do it. Whatever. X to the 4th minus 17x squared plus 16 equals 0. Now, immediately, what's different? Higher degrees. There is no x. There is no 3. But remind me, why did we put an x here and an x here?
So that
Because how many did I have?
2.
Okay. How many do I have now in this equation? So how many am I going to put in each little dude? So we actually do this the exact same dumb way we did this. And why does this work? Because when I cut this in half, I get x and x, and that goes into making the correct middle term. If I break this in half, do those become parts that make the middle term work?
Yeah.
So what's got to be true in general for this middle power? It has to be, you could do it. The middle power has to be how related to the first power? It's got to be half, because what's the first thing we do with the first power, dude? Cut them in freaking half. So if that was a 10th power, this would have to be a 5th power. Half a 10th. Because again, what would I do with x to the 10th? I would cut it in half. It would become x to the 5th. That would go into making the middle term. I really want that to be understood. This is something called quadratic in 4. Because it's not quadratic. It's a 4th power, not a 2nd power. But let's keep going. What numbers work?
-1,
Yeah, -1, -16. Can I continue factoring? Both of them. How do you factor this guy?
4, -4, positive 4.
So what are my 4 answers?
1, negative 4.
Yeah, 1, -1, sure.
Positive 4.
4. Why is it not surprising I got 4 answers?
Because you're higher, smaller degrees.
4th degree, yes. Now I could have gotten 4 1s as an answer, but I still get 4 answers. Like maybe some are repeats. So that's the fundamental theorem of algebra. Sounds kind of important. Whatever the highest power I see in the problem, I should get that many answers. Some could be complex, some could be repeats, but I get that many answers. So you have a whole slew of this kind of problem where if I put an 8 there, there has to be a 4 there for that to work, yes? Okay. Here's another kind of problem. Let me see. I don't think we've done a problem like this directly, but let me see your reaction to this. Oh my God! Let me see. Sorry. Shut up, Jeff. That was my own joke for myself. How do you think you would solve this equation?
Maybe rewrite it as to the 1/2 power.
Square root, yeah.
Oh, yeah.
So the main problem is my variable is stuck inside of the square root. If my variable is ever stuck somewhere, I try to kill that thing. Or if it was stuck on the bottom of a fraction, I would multiply and get it unstuck. I want to unstick it somehow. So the most direct way to unstick this dude is to square both sides. So the biggest mistake I see is people start to FOIL over here. Why does that not make any damn sense? Because what does the 2 immediately do? Cancels. Don't make this harder. And what's 2 squared? Holy shit. So then add 1, divide by 3, blah, blah, blah. Who cares? Okay. All right. So let me take this to the next level. There's always another level. What if I had Ooh. Okay. What the shit, Jeff? So you were trying to take me the direction of fractional powers too soon. I was like, no. So if I just have square roots, I don't need to make them fractional powers. I just square, right? Cube roots I cube, blah, blah, blah. This is a little more complicated. But what do the X is pretty cool. He's up top. He's sort of stuck inside of a 4/3 power, but I want to kill the 4/3 power. Do I take a 4/3 root? Thank the gods, no. Can you guys remind me real quick, a little side note, what would this be? Nope. 15. Because that's 5 groups of 3x's.
Yeah.
And that's the definition of multiplication, yes?
Would you raise everything to the 3
Kick ass. I know whatever power I put here, I'm going to multiply it, and what I want that power to become is a 1 power, yes?
Yeah.
So what do I multiply any fraction by to make it become 1? Reciprocal. So I better do the same thing to both sides. So this becomes 1. I did half of it. What does that become?
Well,
We've talked about fractional powers before, yes?
kind
Shit. Have we talked about fractional powers before?
of. Yeah.
Okay, thank the gods. I'm very sorry.
I remember how.
I teach classes that have almost the same material, which drives me crazy sometimes. Do you remember what's on the bottom of planes? Planes. What's on the bottom of planes? This makes me feel like I haven't talked about fractional powers. Planes. Roots are on the bottom of planes, correct? Most planes. Don't come at me with technically, I've got actual glasses. Technically, Jeff. Tubers are, no, shut up. Most plants have roots on the bottom. So what root am I taking? What's on the bottom?
16.
It's the 4th root of 16. So what does it take 4 of to multiply by 16? 2. So the 4th root, so I could rewrite this as the 4th root of 16 cubed. 4th root of 16 is, what does it take 4 of to multiply by 16? 2. And what's 2 cubed? 8. Done.
I don't know if you've seen it done that way.
Oh, okay. There it is. Okay. And then, what about, what does this mean? So we've graphed these things. I'm pretty sure haven't we solved equations with these things?
Yeah.
Remember, this is where you have to write the 2, we've even done inequalities, correct?
It'll always be.
Look at this go. The haunted house and the restraining order. Does that sound familiar? Okay, I'm sorry. I went too far. Basically, it's related to this. This means stay close to me. The distance between you and me, I want it to be less than 7. And this would be a restraining order. You must be at least 7 feet away from me. But okay, don't worry about it. That's not part of section 2.6. We're fine. And we've already done absolute value stuff. I just forgot. Here's the last kind of problem. And then I've got a little worksheet, which is a complete surprise. How the shit? I'm going to do 2 problems in a row. I'm going to call it A because I'm tired of Roman numerals. How would you solve this equation here? Don't overthink it. Cross multiply, yeah. 7x equals 3x plus 3, 4x equals 3, x equals 3/4. Now, what if I have an equation that's got more fractions in it? And you know I'm going to do that because there's a load of fractions. So what if I had this equation? Oh my God, Jeff. Why? Come on, man. All right.
Back to the bottom.
Sure. So here's the thing. What I really should have started with this different problem. If I have fractions in an equation, my immediate thought is to kill them, because if I have an equation, I'm allowed to do stuff to both sides. So whatever will make things better I can do that as long as I do it to both sides. If I multiply everything by x minus 1, will one of my fractions stop being a fraction? Yeah, this first one, the x minus 1 will cancel. Will he give a shit? No. If I multiply everybody by x plus 1, he'll stop being a fraction, but he won't give a shit. So what do I do then?
You can multiply by both.
Multiply by both. I overkill some of them. I just want them all freaking to stop being fractions, yes? So if I multiply everybody by x plus 1, x minus 1, and notice what he is.
Equal to that.
Yeah, so these would cancel, yes?
Yep.
What happens here?
You get the x minus 1
Yeah. And then what happens here?
plus 1
Die. So I get 2x plus 2 plus 3x minus 3 equals
5x.
5x. Now, immediately, that looks stupid amounts better. That first equation looked like, stop doing that, Jeff. Erase that shit. And now all of a sudden, okay, I made this a little bit harder. By accident, I made this harder than I wanted it to be, but that's okay.
Very quickly hits 0.
So you guys, all right, this specific problem has an issue, yes? What is the answer? What's the answer? Is this ever true? So there's no solution. Thanks, Jeff. All right, so let's do this. So any problem like this for us, you will pretty much always, the one thing will always factor to be the other things. It almost has to be, or else this will become so much worse. So let me give you this. And take a look at it yourself for a bit. And then I'm going to try to do something I haven't done yet with you guys. Which I don't know how you feel when I say that, but let's see how it goes over. Capture some of the work that I know you guys all got right. What's really neat is you guys can all I always forget how many monitors I have in any given room. So half of you guys can see the forward monitor and half of you guys can see the other monitors. Okay. I believe everybody got this one. There's one little thing that we're not done with on that, but I want to wait until I got everybody. This one I'm not certain about, if everybody got this. Ah. Okay, and I think some of you guys are working on part E right now. So, guys, I know some of you guys are not quite done, but I want to talk about this one real quick. And you can watch up there if you want to. If I look at the original problem, doesn't this say square root equals number I don't know? What is wrong if I get an answer of 4, for example? Can anyone see what is wrong if I get an answer of 4? What would this say? The square root equals, what's 4 minus 5? So can the square root of something equal -1? No, why not? Because by definition, this is the positive root. So do you agree that there are some values of x that would automatically not work? Okay. If you did everything right in this problem, you got these two answers, yes? 10 and 2. You did everything right. But for some reason, when I plug 2 in, it doesn't work. But what we just said was, if x is 2, for example, I get a negative number. Now, I really want this to be understood. As a student, is anyone perturbed that you did everything right and you still got one of your answers was wrong? Does that frustrate anybody? Okay, here's the trade-off. Math, as far as I know, can't tell us shit. It can't actually whisper to me, hey, you up there, this ain't gonna work. So, when we squared, if this was a negative number, what would it have become? Positive. So the only way we could get any answers was to square. But the minute we squared, we lost information about if that was negative or not. So the two answers we got work in this equation. They don't work in the original equation. So the only way I could get any answers opened the door to some wrong answers. So we just gotta live with that shit. It's not that we did anything wrong. It's not that math sucks. You can think that for other reasons, but this one is not valid. It's that the only way we could get any answer allowed for some wrong answers to sneak through. So that's a trade-off. I want to get the right answer. I got to accept that some of them might not work. So what do I do? Whenever I solve a radical equation, I check my answers. I make sure that neither one of them, this one didn't work, throw it out. Okay, maybe. And then I was telling somebody about a shortcut to this. Let me do this the long way and then see if you guys can pick up on the shortcut. How do you factor this one? Like these two, yes? So almost always that's going to happen. So if I multiply everything by this, good Lord. Okay. Both of these die. This one dies. This one dies. Now, that's a lot of writing, blah, blah, blah. But here's a shortcut. If I look at it again, I know I'm going to multiply by this and this. So whatever it doesn't have is what it's going to pick up. This guy has both. He doesn't pick up anything. Get out of there, plus. Or get in there, plus. This guy's got an x minus 2, so he's going to pick up the other guy. This guy's got an x plus 2, so he's going to pick up the other guy. And that's exactly what we just got. This idea of they're going to pick up the other one that the bottom didn't have, because that's what's going to be left alive. That's a bit of a shortcut. And then you get this beautiful linear equation. Yes? No bottoms. So I get 3x and 2x is 5x. 4 plus 5 is 9. I get x equals negative 17. Yes? One little thing about this. What could x not be? 2 or? So if I got either one of those, I would have to throw it out. Okay. Is everybody with me? So this is section 2.6. All of these kind of problems are in section 2.6. And I can't remember, it's on the homework sheet, but it's from way earlier, yes. It's something I skipped before, and I just couldn't figure out where to shove it. So I decided, shove it at the end. All right. It's so weird. That's pretty much all I have for today. So, tomorrow is what's happening. Review for the final part one. So it's gonna be some group work of some older ideas. Then over the weekend, I'm hoping you guys try to practice this out, and then next Tuesday, it's gonna be open review for whatever questions you come with. That's plenty. Tomorrow, I'll try to have some stuff graded for you. Yesterday was a long ass day. It's always fun to be in the room below this when that's happening. Ridiculous.